In this video, we're going to talk about the ideal gas law and the kinetic molecular theory of gases. The kinetic molecular theory of gases lays out some basic assumptions, simplifying assumptions about gases. 4 simplifying assumptions about gases. Gases are small particles that fly through the air. They are not in contact with each other. They can expand out indefinitely. They can also be compressed, unlike solids and liquids. So these are 4 simplifying assumptions to help make calculating the behavior of gases easier and less complex than real life. An ideal gas is a theoretical gas that abides by these 4 assumptions. So we're going to call those ideal gases, and we're going to treat all gases as if they are ideal, or we're going to assume ideal behavior. Number 1, ideal gases have 0 volume. Again, this is not reality. This is a simplified assumption. When we talk about gases occupying a volume of space or occupying a container, we're not going to consider the volume taken up by the gases. So they take up no space, and there's no need to subtract the volume of the gas particles of an ideal gas from the total volume of a container. This also implies that there are no repulsive forces in ideal gases. Number 2, the kinetic energy of an ideal gas particle increases with increasing temperature. As you raise the temperature, the energy of motion of the gas particle increases. Basically, gas particles speed up. They start to move faster. Gas particles already move incredibly fast at hundreds of meters, if not thousands of meters per second. That's faster than any bullet. Kinetic energy is the energy of motion. It's the energy of movement. The formula for kinetic energy, in case you're interested, is 1/2 mv squared, where m is mass and v is velocity. We're not going to make use of that formula in this class. That's a little bit beyond, not really too relevant to our topic. Number 3, ideal gas particles have no attractive or repulsive forces. So they don't attract each other. Again, this is not like real life. In real life, gases do attract one another, and they can also repel if they're pressed too close to each other. They are considered completely inert. Number 4, ideal gas particles are not in continuous contact. So unlike liquids and solids, gas particles are not stuck together. They're actually freely floating in space. They do collide with each other. That's the limit of contact between one gas particle and another, is they slam into each other at high speed, but when they do, they bounce off without losing any energy. They'll also bounce against the inside walls of a container if they happen to be contained inside of a tank or some sort of vessel. There are some differences between real-life gases and ideal gases. The ideal gas law and the other simple gas laws make predictions about gases which hold true for most conditions that pertain to everyday life, meaning if you're close to room temperature, even down to freezing temperature, and when I say freezing, I mean the freezing temperature of water, and around atmospheric pressure, the ideal gas law and the other gas laws, well, actually the other gas laws predict the behavior of gases pretty well in any case, but the ideal gas law can make fairly good predictions. There's very little deviation from the ideal gas law under normal conditions. It's small but insignificant. So temperature and pressure and volume play a big role in determining how much variation or how much deviation from ideality real-life gases will go, depending on conditions. I said that. Okay, at pressures and temperatures close to atmospheric, most real-life gases only deviate slightly. Under extreme conditions, you'll start to see more of a deviation away from ideality. Also, the identity of a gas has an effect. The ideal gas is a non-identified gas. It doesn't really matter if you're talking about helium or hydrogen or xenon or argon or any other, or carbon dioxide. If you're describing an ideal gas, their behaviors and properties are all identical, because the ideal gas law does not make a distinction between one gas and another. Once you say it's behaving ideally, it is one and only one gas. In real life, some gases have more attractive intermolecular forces than others. Real life gases take up space. So that's the very first assumption to fall, is that under extreme pressures or extremely small volumes, which amounts to very much the same thing, the volume of a gas particle and the collection of gas particles actually starts to matter. It starts to become a significant proportion of the volume of space we're talking about. So there you can already see a breakdown in the assumptions. At high pressures, real gases have a larger volume than that predicted by the ideal gas law, because at high pressures, there are a lot of gas particles just sort of squeezed into a small space. Now suddenly you have to consider, wait a minute, these gases are taking up some of that very limited space. The ideal gas law, which was up until now considering them to have zero volume, is going to be an error, because now the gases are actually taking up space. So real life is not going to match the ideality or the theory. At low temperatures, at low temperatures, you're going to see the gas particles slow down. Remember, one of the ideal assumptions was that, and this one holds true, the temperature, as you lower temperature, the kinetic energy of a gas, basically the speed of a gas, because the mass doesn't change, its velocity is going to slow down. As it slows down, the intermolecular forces of attraction and possibly even repulsion, depending on the gas, are going to have a greater effect. It's one thing if gases are moving at lightning speed, or at least very fast relative to one another. Their attractive forces aren't going to have much of an effect. They're just going to slam into each other at high speed and bounce away. But if they slow down, that gives that reduction in kinetic energy allows for the attractive forces to take hold, and you might actually see gases sort of group around each other or not bounce off with as much energy as they had before the collision. So just as an object approaching the Earth or approaching the sun might slow down and even slam into the Earth and not move away from the Earth or see its path adjusted, so one gas particle will be attracted to another in real life if it slows down enough, and they might actually sort of start to coagulate together, or at least come closer together, draw closer to one another. That results in less volume or lower pressure. If you hold pressure constant, the volume will decrease of a gas because its particles are going to be attracted to each other at low temperature. We're talking about very low temperatures. There is an equation called the van der Waals equation. The van der Waals equation has empirical factors A and B, they are called A and B, that are specific to real life gases. So each gas has its own values of A and B that you can plug into the van der Waals equation to account for these differences between ideality and real life behavior of those gases. So they're basically correction factors. They subtract volume. Say there's a factor that subtracts a certain amount from the volume to account for the fact that gas particles take up space. So actually less volume in real life than the ideal gas law states. And there's a factor to add back to the ideal pressure to account for the fact that there is a buildup of pressure because gases take up space. And they also have some repulsive forces as well as attractive forces. The van der Waals equation is beyond the scope of this class, so we're not really going to get into the details of that. But just for your information, there have been attempts to correct for these deficiencies in the ideal gas law at extreme or more extreme conditions. But generally speaking, in this class, we're going to assume ideal behavior for all of the gases. We're not going to work with the van der Waals equation, and the predictions that we're going to come up with are going to be taken at face value. So the ideal gas law, pressure times volume equals moles of gas times the gas law constant R times temperature in kelvins, units of kelvins. This is the ideal gas law or the ideal gas equation. PV equals N times R times T. Any gas or its behavior can be completely described with just four variables. Pressure, P stands for pressure, V stands for volume, N stands for moles, and T stands for the temperature, but the temperature must be in units of Kelvin. No other temperature scale will do because only the Kelvin scale is unique in that it is an absolute temperature scale. In fact, it was the study of gases that gave the origin to the absolute temperature scale, the Kelvin scale. That's because every other temperature scale sets the zero bar at an artificially high point. Only the Kelvin scale truly sets zero at a complete absence of heat. The term R is a constant. It does not change. It's not a variable. It's a constant, which I encourage you to memorize. One particular value of R, which we will use here in this class for the most part, is 0.0821. The units are liters times atmospheres per Kelvin times mole. This is not a formula. These are the units. It's a compound unit that happens to be composed of four different units. Notice that those four different units correspond to the four different variables involved in a gas. Liters for volume, pressure, atmospheres for pressure, kelvins for temperature, and moles for N. So there are other values for the gas law constant R, depending on what units you want to use, but since we're mainly going to deal with liters and atmospheres in this class, we'll stick to this value. P stands for pressure. There are several units of pressure, and I want you to be familiar with all of them and how to interconvert between them. And we'll take a look at pressure units and pressure in a moment. V stands for volume, typically expressed in liters only because when you're using the gas law constant R value of 0.0821, that assumes liters rather than any other volume unit. T stands for the absolute temperature in kelvins. You will not use any other temperature scale for any of the gas laws that we talk about. All gas laws rely on an absolute temperature scale. Otherwise, the fractions, the ratios of temperatures that we talk about in these gas laws are going to be meaningless if you use Celsius, or if you use, it's even worse if you use Fahrenheit. N stands for moles of gas. N always stands for moles. We won't really be dealing that much with grams of gas because it's hard to weigh gases, though occasionally we will have questions that come up that deal with grams, mainly just so we can calculate density or molar mass. But for the most part, you usually want the moles of a gas so you can relate it to the pressure or the volume or the temperature of a gas. So pressure, what is pressure? Pressure is a force spread over some unit area. When I say unit area, I mean spread over exactly one unit of area, whatever that unit is. So pressure as a formula equals force divided by area. You take a force, you take an area, you divide one over the other, and you get pressure. For example, in the American system, we use pounds per square inch for our pressure, PSI. That is not the standard unit, that's the American unit. Like anything else, we're gonna have to convert from PSI to the scientific standard unit of an atmosphere. But PSI literally means pounds per square inch. A square inch is an area. Any squared length unit is an area. Pounds are units of force. We think of them as units of mass or weight, but they are not. They are actually units of force. A pound is a unit of force. We don't notice the difference because on Earth, the assumption is we're taking that unit force and we're multiplying it by acceleration to get, we're taking our unit of, actually we're dividing by acceleration to get our unit of weight or mass. So pounds per square inch, force over area. Other units include the Pascal, which is 1 Newton per square meter. Again, you have your squared length unit for an area, and you have a Newton, which is a unit of force. The pressure exerted by a gas is the sum of all the forces of individual gas particles, individual atoms or molecules, ramming into the inside walls of a container. If you hold a gas in a container, and I'm talking about, of course, gas, not gasoline, but air gas, I guess is the only way I can really describe it. The gas phase gas, the combined force of all those gas particles colliding with the inside surface area of any container is the force, and it's spread over the inside surface area of any container. So that's force divided over area. Pressure can be expressed with several units, and I want you to be familiar with all these units and how to interconvert between them. Now, the scientific standard unit, the so-called SI unit, the International Standard for Scientific Units, the SI unit of pressure is the atmosphere, abbreviated ATM, atmosphere. The atmospheric pressure, or the air around us, is 14.7 pounds per square inch, or expressed in units of atmospheres, is 1 atmosphere at sea level, at sea level. Now, as you may or may not know, as you go up in altitude, as you get further and further above sea level on Earth than probably any other planet, the atmospheric pressure, the pressure of the air around you, decreases. So at the very high altitude, say for example at maybe in Denver, Colorado, or the Mile High City, that's 1 mile up, 5,280 feet in altitude, you will find that air pressure is lower, significantly lower. If you go up Mount Everest, you're going to find that the air pressure is extremely low, only about 0.6 of the value, or 0.6, between 0.6 and 0.7 atmospheres. About 8.4 to 9 PSIs, pounds per square inch, at the top of Mount Everest. So as you go up above sea level, atmospheric pressure decreases. But at sea level, it's almost always about 1 atmosphere, or 14.7 pounds per square inch. That's what you're feeling. You are feeling every surface of your skin, every square inch of your skin, whether you realize it or not, you are experiencing 14.7 pounds pressed against your skin. And I don't mean just in the downward direction. Even the underside, if you hold out your hand, even the underside of your hand is experiencing 14.7 pounds pushing upward. The tips of your fingers, if you hold them out straight ahead of you, they're experiencing the 14.7 pounds of force sideways, upways, downways, in every single direction. You are being squeezed by the air around you. Every square inch experiencing 14.7 pounds. That's how much air is weighing on every square inch of your body, regardless of direction. So here are the conversion factors between the different units. There's also another one down here. 1 atmosphere is equivalent to 14.7 pounds per square inch. But there's some other units, namely the 760 millimeters of mercury. Now, millimeters of mercury is not the unit. Millimeters of mercury, well, it is a unit, but that's a unit. Millimeters of mercury is actually a unit of height, right? Or length, millimeters of mercury. But this is how high a column of mercury will rise above its own surface level when pushed by the atmospheric pressure, or by the local air pressure. We'll actually take a look at a schematic of a barometer, and that gave rise to this sort of measurement. Right now, just take it as a sort of unit without understanding the reason why, but it is a unit of pressure, but the millimeters themselves are not meant to express the unit pressure, but the millimeters of mercury are related to pressure. So 760 millimeters of mercury in height. That's equal to 760 torricellis. and Tor for short, which is Torricelli was an Italian scientist from that studied gases way back when. Then we have Pascal, another French scientist. Pascal, 101,325 pascals. That unit is equal to 760 torr or 14.7 psis. And then you can also, oftentimes it is divided by 1,000, so you get 101 kilopascals. Sometimes you get this megapascals, and gigapascals. In fact, I have an example today. So you will see other metric prefixes in front of the Pascal, and you will have to convert those units. One more unit that I don't make too much use of, but it is common in physics and common in engineering to encounter this. A bar is equal to 100,000 pascals or 100 kilopascals. So a bar is just under an atmosphere. It's 100,000 divided by 101,000, so about 0.9 or 0.9 something atmospheres, or just under, around 14 psis instead of 14.7 psis. So a bar is approximately an atmosphere, just under an atmosphere. And you can convert it exactly by using the conversion factor between bar, kilopascal, and atmospheres. So the gas law constant R uses units of atmosphere. So if you want some other unit besides atmospheres, you're going to have to do some unit conversions. You're going to have to convert from atmospheres to one of these other units if you want those instead. For example, if you're in America, you probably want either PSIs or bars. So you probably want to convert, you're going to want to convert from atmospheres to bar. Also in the United States, we tend to report the barometric pressure, which is the local air pressure. Instead of using 760 millimeters of mercury, it tends to be reported as 29.9 inches of mercury. We actually say this on the news. You will actually, or if you look up the local air pressure, you will see 29 inches of mercury. That's the conversion between 760 millimeters and inches. That's what 760 millimeters converts to in inches. Remember, it's 25.4 millimeters per inch or 2.54 centimeters per inch. So be sure you know how to convert in between all of these units. In fact, let's take a quick example. To convert between one unit and another, again, we just come back to dimensional analysis. So let's just run through some quick examples here. Let's say, for example, my tire pressure, which is actually what's called gauge pressure. Gauge pressure, when you read off your tire pressure, that's actually the pressure above and beyond local air pressure. Your tires don't just have the pressure that you read on the dial. They're actually that much more air pressure than compared to the outside. So your true pressure inside the tire is actually air pressure plus whatever the reading is. So if your tires are at 36 psis, it's actually 36 psi plus 14.7 psi. It's actually more like 50 psi because they have to have enough pressure to push back against air pressure on the outside of the tire. In any case, that doesn't really affect our calculation here. My tire pressure reading was 35.6 psi. What is this in atmospheres, torrs, and kilopascals? So here's the conversion. So we know that, so as always, given a definite quantity and a definite amount, we always start with what we've got, what we know, and we always end with what we are looking for, the unit, and then we'll calculate that. So 35.6 psi, we know that 14.7 psi is equal to 1 atmosphere. We know this because hopefully you'll have memorized that sooner or later. So that means 35.6 divided by 14.7 gives us 2.42 atmospheres. So almost 2.5 atmospheres, 2.5 times the local atmosphere. If we're converting to torricellis or torrs, we take the same relationship. 14.7 psis are equal to 760 torr. Now, you might find it that you might think this is some kind of strange coincidence that 14.7 psi is equal to both of these. But remember, the way I listed this for you over here, 62. So 14.7 also equals to each other. So whenever I invoke PSIs, I'm going to use this same exact bottom half of the conversion factor. The only thing that's going to change with the unit is the top half, depending on which unit I'm trying to convert to. So every 14.7 PSIs is also equal to 101.325 kilopascal. Actually, it's many, 1 bar, 1 bar kilopascals, and we know that 0.325 kilopascals is equal to 1 atmosphere. So I said it was going to be somewhere around 0.9 something atmospheres for a bar. K, kilopascals, divide by 101.325 kilopascals, and that gets us 0.987 atmospheres. So there you go. In fact, here, just so there's no debate about the about the sig figs here. Let's just make it 3 sig figs. So 1.00 bar is equal to 0.987 atmospheres. If we wanted to convert bar to PSI, we could say, okay, well, we have 1 bar. We know if 1 bar, 0.987 atmospheres. And we know that 1 atmosphere is 14.7 PSIs, pounds per square inch. Then we can just take 14.7 times 0.987, and that gets us 14.5. So 14.5, 1 bar is 14.5 PSIs. So there you have it. So just under an atmosphere and just under the number of PSIs at room temp, or actually I should say sea level atmospheric pressure. Okay, the ideal gas law and the standard temperature and pressure. We're going to start with this, but just be aware that standard temperature and pressure, even though it's considered standard, is not at all going to be the most common set of conditions that we encounter for temperature and pressure. Now, talking about the ideal gas law, often you're going to know 3 out of 4 of the variables: pressure, volume, temperature, and moles. 3 of those you're going to know. And so when you want to use the ideal gas law, you're going to use it in situations or scenarios where you just want to know that 4th variable, but you already have 3 of the variables down. You lock them down, you know what they are. So for the variables to define the state of a gas, you just need to solve for that one last one. That's when you use the ideal gas law. Standard temperature and pressure gives you 2 of those in, right away. In abbreviated form, it automatically tells you, oh, your temperature and your pressure are equal to the standard value. So remember this, because is exactly 0 Celsius or 273.15 Kelvin. That is your standard temperature. The standard temperature, note, is not room temperature. Room temperature is not standard. 0 Celsius is standard. In fact, if it helps you to remember this, is Kelvin for any gas law calculation. Never use Plus, you'd find very quickly that you run into a brick wall if you tried to use 0 Celsius or 0, and you multiply by 0 to be 0. So hopefully you'll notice that, and you'll remember, oh, wait a minute, I wasn't supposed to use 0 Celsius. I was supposed to use kelvins. Recall that to convert from Celsius to Kelvin, you add 273 to the Celsius temperature. So the formula to convert between Celsius and kelvins is to take the Celsius temperature and add 273.15. I usually omit the 0.15 and just make my life simpler. I usually just add 273. That's because it has very little effect on any calculation. It's small enough to not matter. So if you want to just omit and just say Celsius plus 273, that's fine. Okay, so 0 Celsius is standard temperature, 1 atmosphere. So it's easy to remember because it's 0 and 1. Standard pressure is 1 atmosphere. Of course, if you need something besides atmospheres like PSIs or kilopascals, of course, it's not going to be the number 1. It's going to be whatever those units are. But if you want a quick way to remember what STP stands for short, STP is 0 and 1. 0 Celsius, 1 atmosphere. But just bear in mind, don't use Celsius temperatures. Use kelvins. Don't use Celsius and then convert the results as kelvins after you're done using the ideal gas law or any gas law. It doesn't work that way. You must convert. Before you enter a temperature into any gas law, you must convert to kelvins before you use the temperature in a gas law. It doesn't work. Once you've stuck a Celsius temperature into a gas law, that's it, it's over. You've already gone wrong. It's already wrong. You have to convert first and then use the Kelvin temperature in the gas law. Okay, let's do an example. At a temperature of 0 degrees Celsius and 1 atmosphere, now just because I'm giving you a temperature in Celsius doesn't mean it's okay to use that. Just remember that. If I try to plug in 0 Celsius as a temperature into my gas law, what am I going to get? I'm going to get 0 for any value I try to calculate, or worse, I'm going to get undefined. So remember, just because I give you Celsius temperatures doesn't mean you're supposed to use Celsius. Always convert to kelvins. Capital K, no degree sign. Don't use degree signs on Kelvin. There's no such thing as a degree of Kelvin. What will be the volume of exactly 1 mole of an ideal gas? Question mark. Okay. So basically what I'm asking is, what is the molar volume, because it's the volume of 1 mole of an ideal gas at STP? In fact, I will often abbreviate at STP. Instead of telling you it's 0 Celsius and 1 Celsius and 1 atmosphere, or telling you it's 273 Kelvin and 14.7 PSI, or however I can express or 32 degrees Fahrenheit and 1.987 bar, instead of telling you that, I'm simply going to say at STP. After this example, N is never going to equal 1 mole again for me. So don't rely on the number of moles equaling 1. No problem I give you. After this example, no problem or question I ask you will ever have N equal to 1 mole ever again. Maybe on the homework because I didn't write all of those questions. But here, I definitely will not include N equals 1. It'll always be some other value. Okay, so to solve this, we know that the formula is PV equals nRT. We know we should use the ideal gas equation because I have 3 out of 4 of my variables. I have the pressure that's equal to 1 atmosphere. I have my volume, which is equal to, oh no, I don't. That's the thing I'm going to solve for. I have my moles, which in this case is equal to 1 mole, N equals 1 mole. And then I have T is equal to, well, it says 0 Celsius, but of course I have to convert. So T is 0 Celsius plus 273 equals 273. And of course I have my R value. But the point is, when I see that I have 3 out of 4, that situation calls for the ideal gas equation. And of course, R never changes. It's a constant, 0.0821 simple units. It's not an equation. Is just, it's just seconds for constant. That's just what it is. It's a compound unit that happens to have units multiple times the size. I just work equals force times distance. So Newton. So let's rearrange. Sorry about that. Let's rearrange. So we'll divide both sides of the equation and onto the right side, so that V is all by itself, equal signs. So V equals nRT divided by B, which we have written right here. Now I am aware I've already worked this out for you down here below. That was intentional, and that's just so you can have this for your notes whenever you need them, even without watching the entire video. Okay, so volume equals N times R times P. We plug in all of our values. We plug in our N, 1 mole. We plug in our R value. We plug in our Kelvin temperature, and we plug in our P atmospheres. And when we do that, we get the value 22.4 liters. In fact, if you want, even though we've already accounted for the moles, you could call this the molar volume. In other words, this 22.4 liters is the volume of exactly 1 mole of an ideal gas. Any ideal gas, any gas behaving ideal temperature and pressure. Now, if you're not at standard temperature and pressure, this will not hold. So you can memorize this number if you wish. It does calculation. But if you forget the number, it's okay because you know the ideal gas. If you forget the ideal gas law, you have to know that. Okay, I was all the units cancel out. So atmospheres with atmospheres, kelvins, how it works. The units of the ideal gas constant R are always going to cancel out all the units except, of course, for the one you want, and that'll carry forward to your final answer. So just be careful. You can use this, this little calculation, you can use it whenever you have STP, whenever you have an ideal gas at STP, and then you need to calculate the molar volume, or if you need the molar volume to relate volume to moles, this is a quick and easy way to do that converting. But again, it only works at STP, so it has kind of limited application. And if you don't feel like you need to memorize this number, that's perfectly understandable. It's not a problem, it's not necessary. You can always recalculate it whenever you need to. Let's do an example where we actually use the result of the molar volume of an ideal gas at standard temperature and pressure. What is the volume in liters at standard temperature and pressure of 0.25 moles of xenon gas? The assumption here is, and oftentimes it'll go unstated, but I'll make it explicit right now. Assuming ideal behavior. Don't let it throw you that I mentioned a specific real life gas, xenon. If we assume ideal behavior, it's always the same gas. It's the hypothetical ideal gas. It doesn't matter that it's xenon or helium. It doesn't matter if it's got 10 atoms or 1. It doesn't matter. It's a gas. So again, we're going to use PV. Well, actually, no, we're not. We've already used PV equals nRT. Now, if you want to recalculate the molar volume of that gas, if you want to plug in N equals 1 and then R value and all that, you can. But you know what? If you memorize that it's 22.4 liters equal to 1 mole of any gas, as long as you're at STP, you don't need to do any more calculating other than the basic dimensional analysis. So let's start with what we know. 0.25 moles of gas. Actually, I'll just put 0.25 moles because it doesn't really matter that it's xenon. 0.25 moles. We know that every 1 mole of this gas is going to occupy 22.4 liters. And that's it. We wanted liters. So 1/4 of 22.4 is, I believe, 5.7. I could be wrong about that. Actually, I think it's 5.6. Let me just double check. 0.25 times 22.4, 5.6 liters. That's it. It's a one-step problem. Now, of course, again, if you did not remember this, it would be easy enough just to plug all of this in. V equals, now this time, since we're calculating for 0.25 moles, it would be 0.25 moles of xenon gas times R, liters atmospheres per Kelvin mole, times our temperature, which of course is going to be 273 because that's the standard temperature in Kelvin, divided by our standard pressure of 1 atmosphere. So we plug all of that in and we get exactly the same thing. Let's hope, right? 0.25 multiplied by 0.0821 multiplied by 273. That gets us to 5.6 liters of xenon gas. Oh, and I should have probably put xenon up here. All right. So you see, they give you the same thing because you've already, in essence, you've already done this calculation. We did it for 1 mole, but now you're just multiplying that 1 mole times 0.25. So it comes in handy to simplify or speed up your calculations, but again, only at STP, only then. Now, if you wanted to memorize, if you wanted to do a bunch of calculations and memorize gas laws for all volumes or other conditions for other sets of conditions, scenarios, that's fine if you wanted to do that. Okay, let's take another example. Let's get away from standard temperature and pressure. Let's calculate some other conditions besides the standard. What would be the pressure, P? So we'll write P down, and that's our question mark. What's the pressure in kilopascals? Okay, so we want kilopascals, so we know we're going to have to do a little bit of unit converting at the end of this problem. Of 0.773 moles, so N equals 0.773 moles. Hydrogen gas doesn't even matter because as an ideal gas, it makes absolutely no difference which gas you're calculating unless you're comparing two different gases under different conditions. At a temperature of 750, so temperature equals 750 Celsius, but remember, just because I give you Celsius doesn't give you permission to use Celsius. We still have to convert. So I'm going to take that 250 and add 273, so I get 1023 kelvins. And that's my temperature. Stored in a 60-liter tank, that's our volume. Liters, remember, our unit of volume, 60 liters. Nothing wrong with liters. We use liters in the ideal gas constant. Assume ideal behavior. This time I explicitly said that you can go ahead and do that, but you can always do that because we're never going to deal with non-ideal behavior in this class. So we're solving for P. So we have P equals, we know that the ideal gas law is P times V equals nRT, helps that it rhymes. We just go ahead and divide both sides by volume. So we cancel volume on the left, we get P equals nRT divided by V. So nRT divided by V. And then we just plug in. So our moles are 0.773 moles. Our R value, as always, is 0.0821 liters atmospheres per Kelvin mole, multiplied by temperature, which was 1023 kelvins. Divide all of that by 60 liters. So we can see that our units are all canceling, except for which unit? Except for the atmospheres. This is the only unit that doesn't cancel. We have moles canceling, liters canceling, kelvins canceling, liters, kelvins, moles. The only unit that doesn't cancel out is atmospheres. So our final unit for this formula is going to be atmospheres. Remember, the question asks not for atmospheres, but asks for kilopascals. So we need to do some converting at the end. So let's plug in our numbers and see what we get. So P equals 0.773 divided by 60 times 0.0821 times 1023. We get 1.08 atmospheres. Oh, that's pretty close. That's just a little bit above, that's just 8% more atmosphere than what we would get at the beach, at sea level on Earth. So pressure is 1.08 atmospheres. Then we have to convert to kilopascals, 1.08 atmospheres. We know that every 1 atmosphere is 101.325 kilopascals. So 1.08 times 101.325 gets us 109. Well, technically, that's about all we should write down because we only have 3 sig figs. So I'm just so you can compare the answer, 109.639 kilopascals. Of course, we should round to only 3 sig figs. That would be 110. The 6 tells us to round the 9 up to 10. 110 decimal place because we want that 0 to count and be significant, kilopascals of hydrogen gas. And of course, you should of course list the gas if you're at all interested in its identity, which the problem did mention it, so you should probably list it at the end. there, even if you don't have to take note of it for the purpose of solving, you definitely want to list it at the end. So just be aware, you're always going to have to do some converting. Most likely you're going to have to do some kind of converting, especially since a lot of temperatures aren't expressed in kelvins. Here's an example where we can actually count or calculate the density of a gas. Now, we don't often think about densities of gases, though they do have different densities. For example, helium is one of the least dense gases, and for that reason, it escapes our atmosphere and doesn't stick around in our atmosphere. There's a reason why, though the Earth generates helium from radioactive decay of unstable isotopes, plenty of helium is in the air, by the way, but it's all traveling out into outer space. Helium, as you recall, is just an alpha particle with 2 electrons added to it. But the helium that gets generated is so light, it's so low density that it floats to the top of the sea of nitrogen and oxygen that's around us. So density does have some kind of role to play, even among gases. As low density as gases are, and they are extremely low density compared to the condensed phases of liquids and solids, there is still a practical matter to considering the densities of gases. So we have 3.73 kilograms of dry ice. As you probably know by now, dry ice is solid carbon dioxide. So we have our carbon dioxide, our dry ice, subliming or sublimating, meaning converting directly into a gas. So inside of a 13-liter tank. So it's trapped in this 13-liter tank. So let's start writing down our variables. Volume equals 13 liters. We have mass. We have our mass is equal to 3.73 kilograms. Now, of course, that's not going to be a direct part of the ideal gas law, but we are going to need that because we're talking about density. And the question is asking for grams per cubic centimeter information. So we know that mass, that kilogram, is going to be related to that gram. So 13-liter tank, once the solid is completely vaporized, remember, that's what sublimation is. It's the direct conversion of a solid into a gas. The pressure of the tank is 2.65 atmospheres, 2.65 atmospheres. And the temperature is -15, but remember, -15 degrees Celsius is not what we're going to plug in. Otherwise, we'd end up with negative values of moles. And so we don't want that. So -15 degrees Celsius. So we take that and we add 273 so that we can convert this to kelvins, 258 kelvins. By the way, you know you've gone wrong if you end up with a negative value of Kelvin, because there is no such thing as a negative value of Kelvin. The absolute zero means that nothing can be colder or even as cold as 0 Kelvin. That's what it is. It is a universal limit to how cold anything can be. It is the complete absence of heat. So you can't have a negative amount of heat. A negative value of Kelvin would actually imply a negative value of heat. A negative value of Celsius just means you're colder than ice, but it doesn't mean you have no heat at all. It's just an arbitrarily set zero point. It doesn't really have any physical meaning. It just has relevance to humans because we care so much about water. Okay, so 258 kelvins. Let's see, 60. Yeah, that looks right. Okay. So what do? How do we get grams per cubic centimeter? Well, remember, grams per cubic centimeter is the same thing as grams per milliliter. Grams per milliliter. Okay, well, a milliliter, so we can convert to milliliters from liters. So it appears we already kind of know half of what this is supposed to be. So we know that we already know that this is 13,000 milliliters. We actually have the bottom half of this already figured out because we know it's 13 liters of volume. And we know 13 liters is 13,000 milliliters, which is 13,000 cubic centimeters. It looks like we've already got this problem set, doesn't it? Except for one thing. How do we figure out grams? Well, we have kilograms, so we can go from kilograms to grams. So we have 3,730 grams for every 13,000 milliliters. Hey, what do you know? Or actually here, let's rewrite it, cubic centimeters. That's it. We have it. So we just take that. In fact, we didn't even need to invoke the ideal gas law. Not in this circumstance, though there will be circumstances. And actually, we're going to do a comparison where we can compare both of them. So we get 0.287 grams per cubic centimeter. That's a low density, certainly lower than water, but as gases go, that's actually fairly high. This gas is a little bit compressed, but of course gases are compressible. But we'll see some other examples where you actually do need the ideal gas law in order to calculate this. Let's say we have another sample of carbon dioxide. But this time we don't know how much. So we use the same conditions, but this time and I'll label this scenario number 2. Same carbon dioxide, same dry ice, but this time we have an unknown quantity of dry ice. Let's say the person forgot to weigh the dry ice. Unknown amount of dry ice left in the 60-liter tank. But this time, the tank is warmed right back up to room temperature. At room temperature, which is, if you recall, 25 degrees Celsius, not standard temperature, that's room temperature, room temp. That's about 77 degrees. Pressure is close to atmospheric, so about 1.71 atmospheres. What is the density of this CO2 gas? So we have an unknown amount of dry ice left in the 60-liter tank. Room temperature, 25 Celsius. The pressure is 1.71 atmospheres, still above atmospheric pressure, but it's coming down. What is the density of this carbon dioxide gas? Now, this time, we actually do care about the identity of the gas. We're gonna need that information, and you'll see why. So let's write down our variables. That's always the first thing to do. And in fact, if you're ever stuck and you don't know exactly how to proceed, write down your variables. And sometimes just looking at the variables you have or don't have will give you a clue as to where to go next. So we have our volume again is equal to 60 liters. And I'm not going to worry too much about sig figs here. I'm just going to write them down. Our temperature is 298 Kelvin. Remember, that's 25 plus 273. That equals 298 kelvins for temperature. Our pressure is 1.71 atmospheres. At least we don't have to do any converting there. And that's it. That's all the information we have. So we have all this. We don't know what our moles are, but we can figure out our moles. Should we figure out our moles? Yeah, I think we should. Why would we need to figure out moles? We still want to know what the density is, right? And we still want to know what the density is in grams per milliliter. Now, we have milliliters. Again, wait, what was this? Did I say, oh, I'm sorry, it's not a 60-liter tank. It's a, well, let's just change the problem here. 60-liter tank. Let's say we have a 60-liter tank. So 60, that's going to be 60,000 milliliters. We have a 60-liter tank. That implies that we already know the volume, 60,000 milliliters. So we have the volume, but what about the grams? This time we have an unknown mass of dry ice. We don't know how much we're starting with. So how do we get our grams? Well, we can get grams from moles, can't we? We always know how to go from moles to grams as long as we have what? What is it that gets us from moles to grams? Moles of CO2 to grams of CO2 is going to be mediated by the molar mass of CO2. Molar mass. Well, what's the molar mass? It's the grams per mole. Well, I already have, let's see, I need grams. I have moles. I have the grams per mole because I know CO2, C equals 12, 2 times oxygen is 32, that's 44 grams per mole. I can figure out moles because I know I have N moles. I have N moles. Well, what's N equal to? Well, isn't N equal to PV divided by RT? Let's see, PV equals N times R times T. If I rearrange this formula and divide both sides by RT, so I get this out of here and I get this over here, don't I end up with N, an expression for N where I know every single number on the left side? So the RTs cancel out. I end up with N equals P divided by R, PV divided by RT. So I have PV divided by RT, number of moles of CO2, and then I can take those moles, and I know that every 1 mole of CO2 will give me 44 grams, and that'll give me grams, and I can put grams divided by 60,000 milliliters to get density. Yeah. That's a lot of steps, and I admit that is a lot of steps, but we can do it. The point is, if you put down what you know and what you don't know, you can often find a sort of trail of breadcrumbs to take you from one to the other, but you have to rely on information on concepts that you've learned before, like molar mass. It's often going to be useful to go between moles and grams. So let's actually figure this out, and let's see what the density actually ends up being. So we have pressure, which is 1.71 atmospheres. Let me use a different color. I don't like this kind of yellowish mustard color. Let's go with blue. So we have 1.71 atmospheres multiplied by 60 liters of volume. Actually, it seems like we could probably even eliminate the 60,000. It's going to cancel with the 60,000 eventually anyway, but let's just take it one step at a time. We can figure out how shortcuts later on. That's not really that critical right now. R, of course, is 0.0821 liters atmospheres per Kelvin's moles, Kelvins and moles, multiplied by the temperature, which is 298 Kelvin. All of this is going to equal N, our number of moles, N sub CO2. So this means moles. This phrase here means moles of carbon dioxide. So 1.71 times 60 liters. Now we don't want to convert to milliliters here because we need to cancel with the units from the R gas law constant. Divided by 0.0821, divide again by 298, and that gets us 4.19. So that's 4.19 moles of CO2. 4.19 moles of CO2. So let's declutter this a little bit. Let's actually work this. Let's actually do a standard mole to gram conversion over here. Forget about all this. Let's just go back to our usual standard operating procedure, put everything its normal way. So here we'll use our dimensional analysis, 4.19 moles of CO2. We know that every 1 mole of CO2 is 44 grams because that's the molar mass or the molecular weight of carbon dioxide. Adding up all the atomic weights, we get 44 grams per mole. So that gets us to 44 times 4.119, 184.5 grams of CO2. Let's unclutter this a little bit. Grams of CO2. So we have this many grams of CO2. That's not our answer. We have this many grams of CO2 in a occupying 60,000 milliliters. So we take our 184.5 grams divided by our 60,000. Remember, milliliters are just cubic centimeters. They're the same unit, really, by a different name. And we get a very, very low density gas, which is about right. 184.5 divided by 60, 1, 2, 3. That gets us to 0.00308 grams per cubic centimeter. A very low density because gases do tend to have extremely low densities. And that's our final answer. So we didn't need to know the mass in this case. We could figure out the mass from the moles, and we could figure out the moles from the ideal gas law. And then we simply use the molar mass to convert from moles to grams, and then get grams, get the density of the gas, take that, divide by 60,000 milliliters. What you get actually, what we basically did is we took P times V divided by RT multiplied by, that gets us N. We took that, we multiplied that by the molar mass, and we divided that number by V. We can actually simplify this if you wanted to. If you're the kind of person who really loves formulas, I'm not, by the way. The reason I love dimensional analysis is because it saves me the trouble of having to memorize a bunch of formulas. With dimensional analysis, I can literally forget formulas like the density formula and other formulas and still find my way because I can always look at the units and figure out whether I need to multiply or divide all the different variables. But if you like that sort of thing, one thing you can do is you can notice that you can cancel out the volume. Since you're actually canceling out volume in both cases, of course, the volume on the bottom is supposedly in milliliters, but let's just say you kept it in liters. You could do that, and you could actually just say, well, it's your pressure times your molar mass divided by RT, and that's it. That's your density. Now, your density will be in units per liter rather than in units per milliliter. So you'd have to do a little bit of converting there. That's the only problem. And if you look at the units, it does actually work out that way. The units of R are liters, atmospheres per Kelvin, moles. The kelvins cancel out. You end up with moles, but the units of molar mass are grams per mole. So if you work out all the units, you end up with pressure units, atmospheres, times grams over moles. Well, the moles are going to cancel out because you're going to have the R value. So you're going to have your liters, atmospheres, and kelvins and moles on the bottom. So let's see what cancels out. Well, atmospheres will cancel out, moles will cancel out, kelvins will cancel out. The only thing that won't cancel out are the grams per. So the only thing that don't well, here we go, zoomed in. The only units that won't cancel out are grams and liters. That's a type of density. That's mass over volume. And if you want to convert from liters to milliliters, just multiply that by 1/1,000, or multiply the liters times 1/1,000. So you could do it that way. You could just take all of this, P times molar mass divided by 1,000 RT. So if you really wanted to simplify this so that you can always get grams per milliliter, it's 1,000 P divided by, oh, excuse me, it's not 1,000 P, it's P times molar mass over 1,000 RT. And that's your grams per milliliter. If you ever really wanted to, if you want some kind of a formula. I do not recommend that necessarily. I think you'll get a lot further if you just understand how dimensional analysis works and how to get from grams to moles and moles to grams. Your understanding will be a lot more flexible. You'll be able to handle any question that comes your way if you can do it the other way, grams per moles, moles per grams. But that is an option for you. You can always derive formulas from an understanding of units. The 1,000 is only there to convert from liters to milliliters. The alternative is, of course, just to remember 0.0821 liters atmospheres could be 1, 2, 3. You could just memorize that as 82.1 milliliters atmospheres per Kelvin mole. It might even be more useful since oftentimes you're using milliliters rather than liters. So if you wanted to just build the conversion to milliliters right into your R gas constant, you could do that. The units are pretty flexible. You can do whatever you want. In fact, another common way to express this is a 8.31 joules per Kelvin mole. That's for energy. Okay, let's continue on. Let's do another example here. Let's identify an unknown gas. So you can actually figure out the identity of a gas by its molar mass, and you can figure out its molar mass again by figuring out the mass of the gas that relates to its moles. So here we're given the grams of an unknown gas, but we, of course, since we don't know what the gas is, we don't know what its molar mass is. But if we can figure out the number of moles, we can get a relationship of grams divided by moles to get molar mass, and then we can search the periodic table for known gases to compare to. And this is a little bit of an Easter egg hunt for known gases. You have to go and look for the actual value on the periodic table that matches your molar mass. But first, how do you get molar mass? Well, you get it by taking grams divided by moles. Well, we already have the grams. We've been given that. The question is, what is our N value? What is our number of moles of this gas? How do we find N? N is equal to PV divided by RT, a rearrangement of the ideal gas equation. What's P? In this case, P is 26.8 PSI. Okay, well, we're gonna have to do some converting. 26.8 PSI, we know that every 14.7 PSIs is 1 atmosphere. That is a conversion factor that I hope you will definitely remember, because PSIs are very common in the United States, and atmosphere, of course, is the scientific standard unit. So we take 26.8 divided by 14.7. We end up with 1.823. Again, I'm using more decimals than I really normally would because I'm not yet at the end of my calculation, so I don't want to round too much. So we have our 1.823 atmospheres. That was the whole point, get atmospheres into our ideal gas expression. Times volume. Our volume is 1,500 milliliters. Well, 1,500 milliliters is just 1.5 liters. 1,000 milliliters is 1 liter. So 1,500 is 1.5 liters. What else do we have? On the bottom, we have R, that never changes. It's 0.0821 liters atmospheres per Kelvin mole. I think by now you can trust that this is going to cancel out all the appropriate units. And then finally, we have temperature of 600. Remember, 600, we have to convert to Kelvin. 600 plus 273 is 873 kelvins. So we plug all of that in and we get our moles of this unknown gas. In fact, I'll even say unknown, N-U-N-K for unknown. N sub something just tells you the identity of that. And in this case, we don't know what the identity is, so we'll call it the unknown. So 1.823 times 1.5 liters divided by 0.0821 and divide again. Remember, any numbers in the bottom, divide. Use the divide key. And then divide by 873. I get 0.03815. 3815 moles of unknown gas. I'll just write it out, unknown. That's my moles. I already know what the grams are. So 3.2 grams per mole are molar mass. That is the definition of molar mass. MM stands for molar mass, by the way, molar mass. Or molecular weight, if you prefer, MW. Molecular. I often abbreviate these, but I guess I should explain my terms here. Molecular weight, MW, MM, molar mass. So that's the definition of molar mass or molecular weight. And so we take 3.2 and divide by 0.03815. I get 83.87 or 83.9 grams per mole. Well, that's my molecular weight. That's not density, right? This is not a unit of volume. This is moles. So this is my molecular weight. Then what do? I go to the periodic table. I go look at the periodic table. I'm going to search the periodic table. I'm doing it since I don't have a periodic table on this slide, and it's very hard for me to actually leave this presentation and come back to it without a whole lot of interruption. I'm just going to tell you, when I search, and you can, you know what, if spoilers, here's my spoiler warning. If you want to figure it out for yourself, pause the video right now because I'm about to tell you what it is. If you want to go and look at the periodic table and try to guess what value closely matches, remember, it's never exact, but look for a value, a molar mass or an atomic mass that's very close to this value. So I'll give you some examples here. For example, let's say sulfur trioxide gas. That's going to have a value of 48 plus 32, that's about 80 grams per mole. That's a contender. I mean, it's close. But let's see if we can find something else. How about chlorine gas? Well, that's about 71 grams per mole, because remember, 2 times 35.5, 71 grams per mole. That's a little too far. Let's consider some other gases. How about single atomic gases? A good place to look might be the noble gases. In fact, let's look at a heavy one like xenon. 131.3 grams per mole, that's a little too much. Too big. I feel like Goldilocks. Some are too big, some are too small. Right now, our best contender is sulfur trioxide. Let's look at one more noble gas. How about krypton? Superman's home planet, Krypton. Let's see what that is. 83.8 grams per mole. I think we have a winner. I don't think we're going to get closer than this. I think even if this isn't it, it's certainly a good guess. This is it. In fact, this is what I intended. 83.8 versus 83.9. There's always going to be a bit of rounding or play here. Don't worry about that. This is basically the same number within error. Within measurement error or within calculation error or rounding error, this is the same number. Remember, our original value was about 83.87. So you actually plug that in, 83.87. That's almost that's the same digit, eight to the right of the decimal. So this is it. So our unknown gas was krypton. So we were able to identify the gas, despite the fact that we didn't know it, we were able to identify it simply by the volume and pressure and temperature of the gas, the volume it took up at a given pressure and temperature. Again, there are many gases that it could have been sulfur trioxide. There are many other gases you could spot this way. Just look for figure out the molar mass and then go searching on the periodic table for either individual atomic gases or molecular gases. So for example, CH4, that's 16 grams per mole. So if we ended up calculating something around 15.9 or 16.1 grams per mole, we could probably assume it's methane. If it's ammonia, it's 17 grams per mole. If it's nitrogen dioxide, that would be 47 grams per 46 grams per mole, etc. So there are different possibilities. Just be aware that sometimes you can identify an unknown gas just by its molar mass. And how do you get its molar mass? You measure its pressure, temperature, and volume, figure out its moles. If you know the mass of gas in that container, then you can take the grams, the mass, divide by the moles, get a molar mass, go hunting through the periodic table looking for it. This is not an answer to anything here. This was just a hypothetical example. So let me get rid of that. So our answer here is krypton. It turned out not to be sulfur trioxide. Sulfur trioxide would be a good guess, but krypton's even closer. So get as close as you can. It won't always be exact. Sometimes there'll be a little bit of play, plus or minus 5% in the measurements. Don't worry too much about that. Just pick the closest value. It's never going to be so close that it'll be genuinely ambiguous for you to figure it out. So that's pretty neat. You can figure out all kinds of information about gases related to their moles. Grams to moles is a big one. It's a big linchpin between the ideal gas law and all the stoichiometry and empirical formula stuff that we've been doing. Kind of links those two, gives a link between those two topics. Speaking of a link between these two topics, stoichiometry. Whenever we've been doing gases up until now, we've been treating gases as if they were regular compounds and talking about the mass of or weight of gas. But generally speaking, you can't weigh gases in a lab. So instead, we talk about moles of a gas. You capture a gas, a certain volume of gas, and you hold it at a certain pressure, certain temperature in a tank, in a sealed, usually metal tank to hold the high pressures of gases. And you look at the gauge on the pressure on the tank. So you'll have like a gauge reading with a little arrow there telling you what the pressure is. 2.5 atmospheres, or maybe oftentimes it's in PSIs or something. And you read that gauge to figure out what the pressure is. That's how you normally store gas, and that's normally how you measure gases in lab. You don't just weigh, you can't put them on a scale and weigh them. So we're going to deal with stoichiometry in gases. Now you might say, well, you're starting off with grams. Yeah, but it's grams of a solid. We're going to see how much hydrogen gas we produce, how many milliliters of hydrogen gas, which is much more appropriate for discussing a gas than grams of a gas. So I had 1.6 grams of calcium metal, 1.6 grams of a solid calcium metal to water. You know that alkaline earth metals react very vigorously with water, not violently like alkali metals, like group 1, but group 2 also reacts right away with water. Those metals react, the water will start to bubble as soon as you drop in a piece of calcium metal into the water, or magnesium, or barium, or strontium. How many milliliters? Okay, so we're looking for volume. What is the volume of hydrogen gas that will be generated from this reaction at STP? Okay, so right there in those 3 letters, we know that pressure equals 1 atmosphere. We know that temperature equals 273 kelvins. That's our STP. And we know that volume is what we're looking for. Moles of hydrogen is what we also need to figure out. How do we figure out moles of hydrogen? I already have an unknown. I have volume. How do I have 2 unknowns in one equation? Well, luckily, I don't really have one equation. I have one mathematical equation, and as chemistry goes, since we are dealing with chemistry, I have one chemical equation, which is just as good. Don't let any mathematician tell you otherwise. So we have 1.6 grams of calcium. Okay, how does that relate to hydrogen? Now, we're not going to want moles of hydrogen. We're not going to want grams of hydrogen. We're going to want moles of hydrogen. So we're going to go from grams of calcium, we're going to convert to moles of calcium because you can't use the chemical equation otherwise. And then we're going to relate that to moles of hydrogen gas. And that's where we're going to end up. We stop right there. We don't care about grams of hydrogen. We're going to take those moles of hydrogen, and then we're going to plug that in over here, and then we're going to figure out the volume from the ideal gas law. So let's take it one step at a time. Work with what you've got, 1.6 grams of calcium. We know that calcium weighs 40 grams per mole. That's the atomic weight of calcium. Just look it up on the periodic table, about 40.1. You know, I like to round a little bit when I'm doing these problems. 1 mole of calcium. Then we go from calcium to hydrogen. This is a 1-to-1 ratio. So 1 mole of calcium gives us 1 mole of hydrogen gas. And that's it. That is our N value for hydrogen. In fact, we'll set this whole thing equal to N sub H2 equals all this. So we take 1.6 divided by 40, kind of wish it were 48 now, or maybe I wish it were like maybe 1 gram. Then it would be easy, it would be 0.025. Oh, actually, it's going to be easy. 1.6 divided by 40 should give us about 0.04. Let's see if I'm right. Yeah, 0.04. 16 divided by 4 is 4. So 1.6 divided by 40 is 0.04. 0.04 moles of hydrogen gas. I told you it would never equal 1 mole again. N will never equal 1 ever again. In any example or any kind of an exam question or any question I give you, it won't, N will never ever again equal 1. So N equals 0.04. Sorry, I'm just picking a color, very critical. 0.04 moles. So then we plug 0.04 moles into N here. So we plug in our values. Volume is going to equal 0.040 moles of H2 times, again, times R. I'm going to stop writing all the other units because it's getting kind of long. 273 kelvins, all of that divided by our pressure, which is going to be 1 atmosphere. Well, that's easy. And so we take 0.04 times 0.0821 times 273. What did we want the units? Oh, in milliliters, right? You know, you might actually just want to remember that this is 82.1 milliliters atmospheres per Kelvin more. It might actually make things just a little bit easier. We end up having to multiply by 1,000 anyway all the time. So we end up with a volume of 0.897 liters. And of course, you want to convert liters to milliliters. We know that every 1 liter is 1,000 milliliters. So that's going to be 897 milliliters, and that of hydrogen gas. So we produce almost 1 liter of hydrogen gas. We produce 897 milliliters of hydrogen gas, and that is the answer to our question. Way down here in the lower right corner, like it's not important. Because it's not. The important thing is that you understand the stoichiometry and how the stoichiometry relates to the ideal gas law. Oftentimes the linchpin, the connection, the junction between stoichiometry and the ideal gas law all centers around N. N is moles. Moles are used in chemical equations and they are used in the ideal gas law and with gases. This is your connection point between the ideal gas law and stoichiometry. Whenever you have a question involving stoichiometry, calculate N. That's the first thing you should think of. What's N? How do I get to N? What do I need to calculate N? And of course, for stoichiometry, your first step is always to write a balanced chemical equation. balanced because those stoichiometric coefficients are critical. Let's do another one. Let's do another ideal gas law and stoichiometry problem. This time, let's start with the end in mind. Let's start with what we want to produce or what quantity we want to produce. And then let's work our way backwards to how much reactant we need in order to produce that much, because that's often the real life question. I need to make this much product. How much reactant, how much starting material do I need to have on hand? How much do I have to go out and buy? So I want to produce 10,000 kiloliters of ammonia for reasons. While nitrogen is plentiful in the air, so I'm not going to worry about nitrogen because 79% of our atmosphere is nitrogen. I want you to remember that to be a well-informed human being, member of the human race on Earth. You should know what the composition of the air you're breathing is. Hydrogen gas is not so common on Earth. So we're going to have to worry about hydrogen here if we want to make some ammonia out of nitrogen and hydrogen. How many kiloliters of hydrogen gas will be needed? Assume all reactions and storage of ammonia occur at 1300 kelvins and 0.92 gigapascals. That's gigapascals. So this is a big unit. Why? Why such high pressure? And why such high temperatures? Because that's really the only way you can get hydrogen and nitrogen to combine. It was discovered a while ago by a Nobel-winning chemist who won the Nobel Prize in Chemistry for this exact reaction, that the only way to really get hydrogen and nitrogen to combine, which is a reversible reaction and mostly falls apart, ammonia mostly falls apart into hydrogen and nitrogen over time. It's not the other way around. They don't naturally want to be ammonia. But you can make this stuff if you keep it at extremely high pressures, not this high, this is actually ridiculous, and high temperatures, and you use something called a catalyst. A catalyst is a substance that makes a reaction happen faster. The catalyst is usually some kind of metal like palladium or nickel, sometimes platinum. These, by the way, are expensive metals. They're more expensive than gold per gram. Anyway, these are your catalysts. It's not necessary for this reaction for me to display this, but I'm giving you some extra information because I want you to be well informed. That's all. That's the only reason. Okay, let's balance the chemical equation. We have 2 times 3 is 6. We have 3 times 2 is 6. So we balance the hydrogens, and guess what? The nitrogen gets balanced as well. N2 and 2 times N, they are balanced. Okay, I'm going to declutter the chemical equation now because even though I want you to be informed, I also want this to be semi-neat, at least as neat as I can get it. Okay, so this is our balanced chemical equation. Remember, anytime you involve stoichiometry, you need these balanced stoichiometric coefficients. Now, let's write down the information that we have and the information, and consequently, the information we need. By the way, we don't need to know that the atmosphere is 79% nitrogen. That was just FYI. That was for your information. I want to produce 10,000 kiloliters of ammonia. In other words, my volume of ammonia is 10,000. Well, actually, you know what? Let's just say it this way, 10 million liters, or 1, 2, 3, 4, 5, 6, 7, or 1 times 10 to the 7th liters. Remember, a kiloliter is 1,000 liters. So we take 1,000 multiplied by 10,000, that gives us 10 million, or 1 times 10 to the 7th liters. Since we're going to be dealing with liters anyway, ultimately, let's just put this in liter terms anyway. So that's our volume. What about our pressure? Well, actually, let's get to temperature first. Temperature is 1300 kelvins. Thankfully, it's already in the unit we want, kelvins. And then our pressure is in units of gigapascals. Remember, we want atmospheres. So pressure is 0.920 gigapascals. Well, how do we handle this? So it's okay, it's no problem. Remember, if you remember your metric units, the prefixes, you know that 1 gigapascal, or giga, any unit, doesn't even matter what follows the giga. Every 1 giga is 10 to the 9th. Remember, a giga is a billion. 10 to the 9th is a billion. 10 to the 9th pascals. Okay, and we know that every 101,325 pascals, if you remember this, now this conversion, of course, comes from memory, not just the prefix, not just the metric system, but every 101,325 pascals is 1 atmosphere. So we can convert to atmospheres this way. And we're going to see that this is a much, much higher than atmospheric pressure. These are super high pressures, the kinds of pressures you'll find on planets like Jupiter or Venus. So I take 0.92, multiply it by 1 billion, or I can simply take 0.92 times 10 to the 9th, and then divide that by 101,325. Don't confuse this with kilopascals. This is 101,325 pascals. And I get 9,080 atmospheres. This would crush a Volvo into a tin can. This would crush metal. This is how strong this atmospheric pressure is, or this pressure is, 9,000 times. Even toward the very bottom of the ocean, you don't get pressures this high, and they have to build reinforced steel submarines just to withstand the pressure. So this is a lot of pressure. Actually, this is an unrealistic amount. You wouldn't apply this to gases. You would actually practically liquefy a gas. You turn it into a liquid under sufficient pressure. Anyway, just take this as a hypothetical example. So we have our volume, temperature, pressure of ammonia. This is of ammonia. But again, these are the conditions for all the gases. So what do we need to figure out here? Well, let's work our way backwards. Since we have a volume for ammonia and we want to work our way to how much hydrogen, let's figure out the moles of ammonia based on this. And once we have moles of ammonia, we can convert to moles of hydrogen using the stoichiometric coefficients of the chemical equation, EQN for short for equation, the chem equation. So let's figure out N first. We know that N equals P times V divided by RT. N equals PV over RT. All I did was rearrange the ideal gas law, right? If you need a refresher here, PV equals nRT. Divide both sides by RT, you get N equals PV over RT. So we put in our pressure, which is going to be 9,080 atmospheres, multiplied by our volume, which is 1 times 10 to the 7th liters. This is going to be a big number of moles. Whoops. Oh, here we are. Times 0.0821. This is in units of liters. That's fine because we're using liters. 0.0821 liters. Later on, we can convert to kiloliters if we want to. I mean, not if we want to, we will. We're going to want to, right? We wanted the answer in kiloliters. How many kiloliters? Times the temperature, which is 1,300 kelvins. This is still going to be a big number. Doesn't matter how big of a kelvins we have on the bottom. We have huge numbers on top. So that's 9,080 multiplied by 10 million, or 1 raised to the 7, 1 times, 1 double E7 divided by 0.0821, that just makes things bigger, divide again by 1,300, and that gets us 851 million, or 8.51 times 10 to the 8th moles of ammonia. That seems like a lot of moles of gas, I got to tell you. This is a lot of gas into a very limited. We can use our stoichiometry. That's not our answer. I don't want to circle because that's not our answer. (8.51) to recognize that we have a mole-to-mole ratio here. Later on, we're actually going to see that we could have done this a lot faster using Avogadro's law. Just by the way. We could have done this in like one step using Avogadro's law, but that's not what I wanted to show you here. So we know that the mole ratio have 3 moles of hydrogen to 3. So 1.5 times 8.5 is going to be about 9.76 times 10 to the 8th, 8.51 raised to the 8th times times 3 divided by 2. It's the same thing as multiplying by 1.5. So that's 1.28 times 10 to the 9th. I don't know if that's what I said, but whatever, times 10 to the 9th. So that's 1.28 billion moles of hydrogen gas. But remember, we wanted to know this in kiloliters. So what do? We take this same number. This is equal to N of hydrogen. And what do we do with it to figure out volume? Well, since this is under the same exact conditions of it's not volume, but of temperature and pressure, all we do is we plug this right back into the ideal gas law, but we solve for V this time. This time we're going to solve for the volume of the hydrogen gas. By the way, I hope you can see that this is actually kind of circular, and a lot of these numbers could actually be canceled out, and we can do this all in one simple step. That's how we get Avogadro's law. But right now, if you can't see that, in a sense, that's good because I want to go through this. I want this to be the example right now. So let's take this. So this is now our moles. So we're going to solve for volume of hydrogen next. Volume of hydrogen equals N times R times T divided by P. So we have our nRT divided by P. Now the N value is the only thing that's really changed here. 1.28 times 10 to the 9th moles. R is always the same value, 0.0821, times temperature, same temperature. Like I said, everything is held at the same temperature and pressure. So 1300 kelvins, all of that divided by the same pressure of, where is it? 9,080 atmospheres. So these two values are the same. The gas law constant, of course, is the same. So all we're really doing is comparing volumes and moles. Volumes and moles, we'll see later, is exactly are exactly the two variables that Avogadro's law deals with, the simple gas law that you probably have already heard of. I wouldn't be surprised. So we take our moles multiplied by 0.0821, multiplied by 1300, and divided by 9,080, and that gets us 15 million, almost exactly 15 million. So the volume of hydrogen gas is going to be 1.50 times 10 to the 7th liters. And then we wanted kiloliters, so that's just going to be 1.5 times 10 to the just divide by 1,000, the same amount of liters, and that's our final answer. Again, crowded down here. More systems, you can use Avogadro's law to simplify this. And we're going to take a look at an example kind of similar to this, where we simplify. We simply take the volume ratios and we substitute those for the mole ratios given by the stoichiometric coefficient. In fact, let's, this is a preview. Don't tell me quickly out of the next video. This will be in the next video with the simple gas laws, Avogadro's law. Let's see if we come to the same example, because this is such a perfect example to show how much easier things are when you understand that all this ideal gas law stuff, although it's great, and it does allow you to make some calculations, when you're comparing one gas to another under similar conditions, or when you're comparing the same gas but under different conditions, all of this stuff, a lot of this stuff just cancels right out. So Avogadro's law would have told us this, that volume of gases and moles of gases are actually, the ratios are exactly the same as long as they're under the same conditions of pressure and temperature. Well, we are under the same conditions of pressure and temperature. We kept those constant. So what that means is that the volume of ammonia as a ratio to the volume of hydrogen exactly equals the moles of ammonia to the moles of hydrogen. These two ratios, now not the absolute numbers, but the ratios are exactly the same. So if I simply plug this in, if I have my volume of ammonia at 10,000 kiloliters to some unknown volume of hydrogen gas, that's going to equal my mole ratio, which is again, my 2 to 3. Well, I already know my mole ratio from the chemical equation is 2 to 3, 2 moles of NH3 to 3 moles of hydrogen. That is the ratio set by the chemical equation. All I have to do then, boy, I hope this works out. I haven't actually tried this before. It should. So the volume of hydrogen is going to equal what? Well, to solve for volume, remember, you can't just divide both sides by 10,000 kiloliters. You have to move the volume up. So I move the volume up, I move the 2 down, I move the 3 across. You can only move diagonally across equal signs. So the volume of hydrogen is going to equal 3 halves times 10,000 kiloliters. That's going to equal 15,000 kiloliters, or 1.50 times 10 to the 4th kiloliters. Look at that. Could have done that in one step. Well, and some algebra. This is called Avogadro's law. You've heard of him. He's the guy that died before the number that was named after him was discovered. But he did do worthwhile work leading to that discovery, or leading to that relationship. He worked with gases, obviously. That's why he has a gas law named after him. So we get the same exact answer. 1.5 times 10,000 is 15,000. 15,000 is 1.5 times 10 to the 4th kiloliters. And notice, by the way, I didn't have to do any kind of converting or anything. In fact, I didn't even have to deal with 1,300. As long as both gases are under the same conditions, they're perfectly relatable. They're perfect. Their mole ratios and their volume ratios are exactly the same. Why? Why, you might ask? Because the volume is equal to nRT divided by P of one gas. If I take the volume of one gas, divide it by the volume of another gas, that's the same as saying nRT over P divided by nRT over P. Well, if R is the same, because it's a gas law constant, if temperature and pressure are the same, everything cancels out except for the moles. That's how Avogadro's, and actually that's how a lot of these gas laws, simple gas laws work. Just cancel all the like terms when you multiply one gas condition, one set of conditions for one gas over another. So that's how you get that. But it was worthwhile going through yet another stoichiometry problem, because there will be times when maybe the product gases are held under different conditions than the reactant gases. I could have easily said that, well, the hydrogen is under a different pressure and a different temperature from the ammonia being stored. And then you might say, okay, well, now I have to plug in and truly figure out a different set of conditions in my ideal gas law for hydrogen compared to ammonia. That would have been a situation where there would be no shortcut. You couldn't use Avogadro's law there because you have two different conditions. T and P wouldn't cancel out in that case, and then you would not have to be able to do this. You'd have to take the ideal gas law and use it twice, once for ammonia and then once for hydrogen. But in this case, I kept them the same. And you can see one step. Avogadro's law, solve for the unknown volume, and you have it. Okay, that is the ideal gas law and a little bit of preview of Avogadro's law, but we're going to have other named simple gas laws: Boyle's law, Charles's law, Gay-Lussac's law, and also the combined gas law, which is actually going to do a lot of work for you, so that you don't have to use the other gas laws. So we're going to take a look at those next time in the next video. I hope all of this was informative. I hope it wasn't too confusing. A lot of it was a lot of steps, and just go over the video slowly. Try to sort of do one step at a time. And unlike me, you might have a little bit more space to work with. Maybe put it in a way that one step naturally follows another, geometrically. Let me know how it's going with you, and if you have any questions or need any clarification. I'll see you in the next video. Take care, all.